All right, thank you. So this is my joke. My undergraduate advisor told me that you should always have a joke in your talk. And so it turns out that this is not just a joke, it's the reality of my life. I grew up on a sheep farm, and so I'm probably one of the only people that can both shear them through a mechanical, through a transformation, and also do it with a pair of shears. So that's my start. Okay, so I'm going to talk a little bit about active materials, but I'm also going to start with an introduction to what I would consider a mechanical phase transition in passive systems, passive fluids. And so I'm a rheologist. So I'm an experimental scientist that does mechanical testing of different kinds of materials, some from biology, some from industry. And so my talk is going to be essentially two parts. The first part is going to be roughly an introduction to the way we make measurements, and then applied to an interesting kind of fluid. And then the second part will be really discussing this sort of swimming spaghetti that you see in the background here. And so there won't be very much math. I feel like that's probably a good thing, because I'll probably get the math wrong. But we do apply some models that I've heard spoken about in this conference. So thank you all for having me here, and thanks for coming. So again, I'm Dan Blair. I'm from Georgetown. And I'm going to tell you a little story today that sort of can be summed up in one movie. And so this movie was taken in my lab a number of years ago by one of my postdocs. And this is a breast cancer cell, this green blob. It's embedded in a three-dimensional matrix of collagen, which is the stuff that makes us us. It makes up most of our bones. It makes us, we're really good at making gravy because we can break this collagen down into gelatin, and that's what makes things taste good at Thanksgiving time. So you're looking from the top down. This is a three-dimensional micrograph in a confocal microscope. The purple stuff is the collagen. Those teal streaks and blobs in the background, those are particles of about a micron in size. They've sort of gotten distorted because of the imaging. But a micron-sized particles that are embedded in a well-designed medium that is of linear elastic response. So the gel, this thing in the purple, is attached to that surface, which is down below. So you're sort of seeing it top down. So the cell is embedded within the three-dimensional matrix. The three-dimensional matrix is attached to a two-dimensional surface. And that two-dimensional surface has fiduciary markers, and I'm going to play a movie here in a moment, that will distort elastically when the cell makes its way through this medium. So here we go. So that's the setup. The cell is probing its world. It's mechanically figuring out what it's in contact with. It's trying to traverse this three-dimensional matrix. And in doing so, it's distorting this bottom material in a way that we can determine what the stress is dynamically as this cell transforms its shape and its position. So this is sort of metaphoric, I think, for what we do in my lab. There's biomaterials, there are measurement methods, there's microscopy, there's dynamics. There's lots of different kinds of things that we're interested in sort of summed up in this one picture. Now, we're going to take a more reduction kind of approach here, where I'm going to use different techniques and different materials that are found within this image, or these series of images, and I'm going to utilize them both to make measurements and to also do some physics. Okay, if you have more questions about that, I'm happy to talk to them. All right, so first thing I'm going to talk about is this idea of shear thickening. And shear thickening is something that if you've watched YouTube ever in your life, and so that's probably all of us, you may have seen kids running across swimming pools of stuff, and where the stuff looks like a liquid, and then they run through it, and it's solid-like. This is oobleck, everybody's favorite stuff from your local kids' science fair. We actually study that. That's our material of choice. And that material undergoes a mechanical transition from a liquid-like state to a solid-like state through an external perturbation. And so we push on it, and it becomes a solid. If we go slowly, it's a liquid. If we go fast, it's a solid. That's the sort of takeaway. The question is why? What is going on inside of that system that allows it to undergo those sorts of transitions? And I'm going to have to take you through the story of these materials, but first I'm going to show you, of course, a YouTube video. This is the backyard scientist. He's a nice guy. This is a balloon filled with oobleck, so cornstarch and water. And he's going to shoot a little projectile out of this at high speed, and it's going to hit the balloon. And in doing so, what I want you to see is that, maybe I can pause it, the material looks solid. But as soon as it starts to fall under gravity, you can see these things rounding up. Look at these shapes. They are really becoming a liquid again. You took the force away, and the material itself undergoes a mechanical phase transition. It's become a different material simply by releasing the constraint of the force. And so these things will form balls, and once they hit the ground, it turns out, if you ever do this at home, they will fracture. You get liquids that fracture. So it's a beautiful experiment. I recommend trying it. Just don't do it in your house. Okay, so what's going on? What's responsible for this? And it turns out the mechanisms happen at lots of different kinds of scales and with lots of different kinds of materials. But the one material that we're most interested in that does this, the thing that was responsible for that image or that movie, are these little particles called colloids. And colloids are, they're all around us. They are the pollen in the air that gives us, spring hay fever. They are the thing in your toothpaste that makes it polish your teeth. They are really an industrial material. And we use them at scale every day throughout our lives. They are everywhere. We use them as models for fluids. So you can imagine that this is 1 micron. Each one of these is about a micron in diameter. They're fluorescently labeled. I can watch them in a microscope. They undergo Brownian motion. They will self-assemble. Some have even perhaps conjectured that they were the reason that the origin of life maybe took place. They had amino acids on their surfaces. They got together and formed complexes. But colloidal scale materials are in the middle, the mesoscale. They're not quite atoms. They're not quite granular. They're somewhere in the middle, and they undergo their own motion due to thermal fluctuation. So they're a good model for statistical physics, and they're a good system to study mesoscale behavior of things like fluids. So I'm going to state that these are my macroatoms, mesoatoms, and I'm going to treat them as the fluid elements themselves. So they are going to be like the atoms in my solution. The fluid in the background, that just provides the temperature. Okay. So the central dogma of colloids have been around for a long time. We have tires. The earliest things were lattices, paint that we spread on the wall. Those are colloids. The central dogma of colloid science was that colloidal particles stick when they are in contact. It's a very simple model, a very simple picture. And that is that if I take these two particles and I put them together under a force, once they make contact, van der Waals says, pulling them back apart, here's van der Waals himself, he says, no, you can't do that. And there's always going to be a minimum associated with physical contact, touching. And it's true. It's absolutely 100% true a lot of the time, and there are examples of it all over the place. In fact, every wall has it on there. This film of particles that was liquid that you spread on the wall. You draw off the solvent, the room stinks for a day, you come back, and it's a solid film. There are things like cheese. I like cheese. Cheese is fat globules that you take off the whey. What's left over is this solid-like material that makes everybody happy. So what happens if we shear these colloids? What's going on in these fluids? So for hundreds of years, literally, the idea was that if particles touch, they can't actually physically touch, because once they do, they're stuck. And you can observe this in the lab as well. But then there was a question. What happens, what describes this behavior that you see in oobleck? Because the physics of the actual interaction, if it's purely a hydrodynamic interaction, that is, the particles come together, there are fluid elements in between, that doesn't describe the phenomenology that we see. You just can't get there with hydrodynamics. You need something else. And the question is it friction? Do I break down all of the years and years of chemical engineering and say, we physicists, we can do whatever we want, we'll call it friction. Is that possible? And it turns out the answer is yes. So the way we investigate this is through this mechanical testing. We put our sheep in the blender, not literally, but we take this measurement called rheology. And we've all seen this, freshman mechanics. First thing you learn is that stress is related to strain. This is just Hooke's law. If you imagine that you have something that's fluid-like, you've taken maybe fluid mechanics, you have Newtonian materials. If the stress versus strain rate, those both give you lines where the modulus of the material is the slope of this line and the viscosity of the material is the slope of this line. But that's a boring world. That's just like, springs and honey. It's kind of boring. But a lot of materials have different kinds of behaviors that's not just in the middle, right? Newtonian is flat, if I look at the viscosity versus strain rate. Some materials will get thicker. This is the story today. This is mayonnaise, everybody's favorite. So mayonnaise is a shear thinning fluid. I started off as a solid. I take it out of the material, the container. It's on a knife. I can turn the knife over. It's a solid-like material. I make it flow on a piece of bread. That's shear thinning. Shear thickening is the other direction. You don't want to get, and the cool thing is that both colloidal systems will shear thin and shear thicken, just depending on the concentration. So if they get the toothpaste wrong, you're never getting your toothbrush out of your mouth, because as soon as you go to pull it, it'll solidify, and then it doesn't come out. So you got to get it right. Okay, so there's lots of engineering that goes into making materials like this. Here's what it looks like in practice. So this is an actual experiment. This is not to scale. This is a tool that's been precisely machined, and it will spin around. So a rheometer, the material, the thing that you're looking at here, measures the viscosity or the viscoelasticity of materials. And what it effectively is a bottom plate that's very flat and a stick blender that's extremely precise. And that stick blender is going to spin around, and I'm going to put some material in between, and I'm going to measure the force response curve. It's basically mechanical spectroscopy. And I'm going to look at how this material responds to that force that I'm going to apply in a circular way. I always equate rheometers to if a Swiss watch and a blender got together and had a child, that's what a rheometer is. It's an extremely precise device for measuring forces. Okay, so here's how this works. The material that's in here is a colloidal suspension that shear thickens. And you can see the material itself is actually acting a lot like that oobleck that we saw, where it roughens this outer boundary. It's almost trying to eject itself from the tool. And as soon as I stop it, it will go back to being a liquid again. So it undergoes this, again, this mechanical transition from being liquid-like to solid-like and back to liquid-like again, just by the application of a force. Okay, so that's going to repeat. You can see it. That's just a colloidal suspension being sheared. There's a lot of shear at the edge, so it kind of wants to shear a lot. It solidifies, pops out. All right, so what does that look like as a graph? Well, here's your viscosity. Viscosity divided, the viscosity of the thing I'm measuring, divided by the background fluid, so water. And so, as you can see, if I have very, very low concentration of those particles, this is like your toothpaste, it's going to act a bit like a Newtonian fluid, may even thin a little bit. If I increase the number of particles per unit volume, you can see that the viscosity starts to go up as a function of the shear stress that I apply. And so the higher the force, the larger the concentration, the more response I get from this increase in viscosity. And in fact, this is, if I plotted this versus shear rate, this would be divergent. This would diverge at a given shear rate, and it would mechanically undergo a transition from liquid to solid. It becomes a solid. So the viscosity diverges at that point. This is just a little bit easier way to graph it. And so this was published a few years ago in PRL, not a few these days. Oh my gosh, seems like a long time ago. At low concentrations, it's very much a hydrodynamic picture. Particles are moving relative to each other, embedded within a fluid. At higher concentrations and at higher shear rates, those particles start to interact in ways that can lead to mechanical instabilities that I'm going to talk about. And there's modeling that's been done. There's some questions about, how does this transition occur? Where does it occur as a function of the concentration? There's a lot of modeling that's gone on. Wyatt and Cates have a picture. This is Mathieu Wiart's work from a number of years ago, about 10 years ago now. And there was a really interesting question about what's the way in which this material undergoes this transition. And so the way they projected this was they said, if you look at the viscosity of the material has to undergo an event where the number of these contacts that we're going to call frictional increases as a function of the shear rate and the concentration. And at some point, the fraction of frictional contacts has to go up to a point where the material becomes a solid. And that is a very nice but very flawed picture in the sense that it's a mean field approach. There's only one number, this F parameter that's here, that says that your liquid is going to undergo a transition from solid to liquid controlled by this simple parameter. It says nothing about how it's spatially or temporally organized. It just says it's going to do it. And so that was very dissatisfying in the sense that, the Lucasian chair of mathematics at Cambridge University says, that's what's going on. You believe him, of course. Mike Cates says things and you believe Mike. But, I just love the fact that I get to tell Mike that he was wrong. And that's very satisfying for me. But you got to prove it. You got to show why. And so that's what we did next. And so remember that movie that I showed you that had the cell that was moving around and distorting that bottom layer of elastic material in a way that was very well prescribed by elasticity theory? We could just measure the forces that the cell was exerting. I'm going to take that technique now, and I'm going to turn it into a rheology experiment. And that's what the core of the rest of this talk will be, or at least this half of the talk. So I'm a microscopist and a rheologist, but I want to do them together because together is better than apart, right? I can't see inside of my rheometer. I could show you the edge, and it looked very cool, but I don't know what's going on inside. And so I decided to take my rheometer and connect it to a four-dimensional microscope, 3D in space and 1 in time, and that allowed me to make movies of what's actually happening in this system. And so we start with a glass cover slip, which is very flat. We put a material onto that cover slip, which is essentially rubber. PDMS is the stuff that they make those high temperature scrapers for your kitchen, those rubber spatulas. But it's clear, so you can see through it. I embed little particles inside of it. These are my fiduciary markers that tell me if the material distorts, what's the displacement. And then I bring in my colloidal suspension, and I place it on top of there, and bring my rheometer tool in place. And now I can twist that tool while simultaneously looking at what's going on using a microscope. And what we get out of that is some beautiful imaging. We developed this technique with some colleagues in Zurich. And these are the details. It's not important. The details are really for material scientists, which I hope none of you are. But the idea here is that we start off with these tiny little particles. They're a micron in diameter. The boundary itself has a stiffness, which I can characterize. And the markers, the thing that tell me how the boundary is distorting, are about the same size as the particles themselves. And we can vary all of that. So again, this standard model, if you will, for shear thickening, which is kind of a silly thing to say, is that at some point, as the shear rate goes up, the system has to find itself diverging. This is the stress versus the shear rate. The system undergoes a transition where the shear rate actually goes backwards because I'm slowing the system down. It's solidifying at this point, and I can't shear it any harder. And you get these interesting S-shaped curves. There's lots of details about this, which is not really all that relevant for what we're doing. But it's to say that there's a standard picture for how these materials should undergo a transition experimentally, and now, if you introduce friction, theoretically. Okay, so again, there are questions of, is this enough particles in a simulation? Details. If you want more details, let me know. it's just to say there's an industry now that has sort of built up around trying to understand this from a computational and theoretical point of view. And it's an interesting problem. Still one that I don't think is quite resolved, and I'll tell you why. Now, this idea that the fraction of frictional contacts, the how many are participating and where they are participating, is sort of a weird thing. There are two types of shear thickening. I'm going to make the story even more complicated to say that there's an idea that there can be a continuous type of shear thickening where things are just sort of flowing still, but shear thickening, and things that can jam completely and turn into a solid and break. It's like when the oobleck hits the floor and breaks into two pieces, that's a solid. It's a solid material that's undergone a transition to discontinuous shear thickening. I'm going to say that's baloney. I won't use the pejorative. So I don't think that's real. I think the idea here is that the number of regions that have undergone discontinuous shear thickening grows until it fills the system. And that's what I'm going to talk about now. So let me set that up. So here's our system. This is what we're doing. We're measuring these fluctuations in the stress at the boundary. And here's what the boundary looks like. That rubber sheet where the cell was pulling on that elastic membrane, these are those little particles that are embedded in that blue rubber sheet. This is how they look as a function of the stress that is applied. So I apply a stress. I have particles at roughly half of the fluid is filled with particles, half is fluid. So it's a roughly 50-50 mix, water to colloids, 50% by weight or by volume. And I'm applying 1,000 pascals of stress. So that's not very much. It's pretty soft, actually. But as it turns out, I can get localization of stress at the boundary. And again, this is only a couple hundred microns across. This is a very small fraction of my total system. But I can measure at a micron scale the amount of stress that individual particles are applying to the surface. So this is a precision experiment with a very messy system. And so as a consequence, we see that the size of these regions can be on the scale of 1,000 to 200 to 1,000 microns. And in fact, the scale of the stress locally can be very high, 6,000 pascals, 6 times the applied. And it's because I can average all of this. Newton's laws still exist. I just have to say, okay, if I average over all of this region where a lot of it's 0, the average should be 1,000 pascals. The force at the top should equal the force at the bottom. I'm not breaking any laws here. I'm just stating that it can be localized. And not only localized, but temporally unique in the sense that if I look a second later, this is going to change. And I'll show you that now. So the stresses are intermittent. They're very localized. The frequency increases with how much stress I apply. And they propagate in the flow direction. And their size is roughly the size of the gap between the top plate that's shearing and the bottom plate where I'm measuring. And so the scale of these objects is roughly square, which I think makes some sense. Now, high stresses increase with concentration. So the size and the magnitude of these increase with the number of particles per unit volume, which I think also makes some sense. And here's what it looks like for different applied stresses. So at low stress, I get a few of these blips. This basically is the average temporally. If I watch this little postage stamp, I see that there's a blip and then maybe another blip. If I increase the stress applied, I get another blip and a blip and a blip. And I can continue to increase this until I get a lot of blips. I'm basically seeing this happening all over the place all the time. That's my fraction of discontinuous events. These things are solids. They have really high stress. All right, so here's what it looks like. So now what I'm going to do, let me see if I can slow this movie down a little bit. You tell a postdoc to make a movie and they make it really fast. All right, so here we go. All right, so let's back up a little bit. So what you're going to see now is instead of that little tiny postage stamp, we zoomed out. I can see the entire tool. So now I lower my magnification, I shrink down my tool, I put the same material in. This is the tool itself, this circle. This line is moving with the speed of the top plate, circling around. And in doing so, I can now measure all of the stress at the boundary. I'm sort of like the rheometer itself, which is sensitive to that stress, increase. And what you're going to see is that these events are very, very localized and then become global. So watch this. I nucleate an event. This was an instability that formed in my system. It has solidified right here. So locally, I get a solid-like phase. So it's a phase transition that's occurred right here. There was some density fluctuation. Something happened inside of my system. It underwent a transition. And now as I let the shear continue, look what happens. It bifurcates. It turns into two objects. One stays where the event started, and one is now attached to the movement of the plate. So as I move forward in time, this one's moved backwards. There are particles, right? So it'd be like all of us running through this room together, holding hands, or running through, a corridor. We have to move. We're being forced to go. There's no way that we can stop. We're getting pushed. So there's a jam that happens here. This thing jammed up. There were particles flowing in from this side to this object. And in doing so, it built up stress. This is the stress, not the particles. So the signature of stress is moving backwards, which means that the particles are being advected into that region, and they're increasing the stress locally. These regions are moving with the tool, and in fact pushing the stress forward, as you might expect, but that means they're attached to the top plate. So I have two species here. I've got one that's on the top and one that's on the bottom. That's what I can infer from this experiment. And when they collide, there's a reason I talked about the standard model, they annihilate. In fact, I have matter and antimatter. And in fact, you can see the signatures of these structures left behind. So you get this pinwheel of stress that's moving now with the top plate. And they persist, and they live long. I mean, there are thousands of strain units here. This is forever in an experiment. If you were to do a simulation on this, every supercomputer in the world would have to be working on this problem for you to do this simulation. It's really hard. But it's consistent. We see this all the time. These events occur. The number of events determines the viscosity. The solidification of the material determines the magnitude of the stress that we measure. And in fact, this is just a very typical day for these sorts of phase-separating materials. Okay, so I'm going to move on. Here's a simple-minded picture. Now you're looking from the side. So instead of looking down on the top, which is what we've been doing, I'm going to show you a side profile of what I think is happening. So this would be the top plate, sort of moving to the right in this case. So I'd be shearing it around. I'd take it and I sort of unfurl it. And I ask, well, what happens to these particles? There's a solid-like event that occurs. This is a solidification event. A phase transition of mechanical, stiffness. I break this object because it's solid, and I'm applying a force. It's got to move. And what you get is you get one thing that's attached to the top plate. It's exerting a stress on the bottom. And you get another part that's sort of advecting particles from this end and maintaining a stress here. The fact that the particles have to go up and over this object means that the stress is really, really high at this point, and that's what you see that signature of. This has stress associated with it because this solid-like phase is attached to the top, and it moves on. Now, this is complete baloney. I don't know if this is true. I'm trying to figure out, that's what we're doing now, is trying to figure this out. And so what we've done is we've changed the paradigm a little bit. Now we're doing sort of high speed, inside the material imaging. We don't look at the stress anymore. We're actually looking at the particles. So these are chimegraphs of the particles themselves. And what we can get from that is local information about the local speed, the local order, the density. And I'm not really going to spend a lot of time. It's a lot of detailed stuff that's really not all that interesting. But it is indicative of the kinds of measurements that we can do. Again, the time step for every one of these little images. This is a chimograph in time. This is 20 milliseconds. So we do extremely high speed photography of a line as the particles move by and start to ask questions about the changes in the local ordering, changes in the local speed, look at the fluctuations as these events occur, and we can check the order parameters, we can look at the speed fluctuations, the intensity tells us something about the local structure. And now we're going to ask questions. Well, if we've got these sorts of events that are occurring and forming and disforming, what does that look like on the scale of the particles? What do we see? We see these very, very rapid fluctuations in the stress as things go by. This region here is like a tiny little piece of one of these bigger blobs. We're going to start to ask questions about how do these things arrange themselves in space. And so within this very long piece of the image, I'm looking at a very tiny singular blip. This is one of my solid-like phases. And within it, there's structure. There's dynamic speed fluctuations that are on the order of milliseconds. And their structure itself is changing that dynamically. It's a really hard problem to start to wrap your head around. And as a consequence, we are going to start to ask questions about, let me go back, exactly what's going on within the material as one of these events forms. What's relate, and we have a lot of details, a couple papers, but I want to get on to other things, so I'm going to just leave it at this. We're going to be able to say with some certainty, how does the structure change? What are the nucleation events that occur to actually lead to one of these bursts of high speed, high velocity, concentrated particles? So that's next. That's what we're working on. Now, the question is, I set it up with oobleck, this cornstarch and water. It turns out you can put that in here as well. And we see the same effect. The same thing happens. These events occur. They persist. This is really high-speed imaging of one of these events forming. That's the tool moving past. You're looking at a very small region, so it looks straight. But the tool is traversing around in a circle. Here's what happens microscopically. So now we've dyed the particles. These are oobleck particles. These are cornstarch particles that have been fluorescently labeled. And we're going to show that these things actually undergo an amazing dynamical behavior. They actually come to a rest. I'm constantly shearing this thing. It came to a stop and does this very characteristic M-shaped movement that we've explored in some detail. In fact, we can even go at another level of speed and accuracy. I'm going to label the particles that represent the fluids, so put some fluid tracers, and we're going to see that when one of these events occurs, when it becomes solid-like, there's actually backflow that happens. The particles themselves do this hoochie-coo, where they go back and forth and undergo a really, really hard to imagine flow profile. There's constant shear being applied here. And these things decide to go backwards. I have no idea what's going on. Please tell me, somebody, write down a model for this. Okay, so there's lots of things to say, lots of people to thank. This is just the first part of the talk. Hopefully I'll get to the second part. But I want to just wrap up a little bit. Shear thickening in most cases, and we actually think all cases, arise from the proliferation of these localized regions of high stress. It is really a local behavior. The high stress regions are associated with strongly non-affine flows. So the material itself has to conform to the local stress state, but it has a hard time doing it because it wants to solidify. Imagine throwing it's like throwing a solid object into a pile of, running or, on the Tour de France, you just throw, all of a sudden there's a car in the middle of everybody and it stops. What do? You got to conform to your local stress state. The heterogeneities involve substantial concentration fluctuations. There are huge fluctuations in the local value of the concentration. This was actually not acceptable a number of years ago. When I told my postdoc advisor, oh, well, the density has to change, or the concentration, he was like, you can't do that. That's not allowed. Turns out he was wrong. The internal structure of these states is highly complex. I mean, we don't have any clue of really what's responsible here. And it is a work in progress that we are still pounding on very hard. Okay, so now it's time for active stuff. Yes?
Like on the picture that you showed before, you can see the blobs and some of them might have different sizes.
Yes.
The size effect of the material itself, shears.
So you can imagine that if you go to a certain thickness of the material, you still see the phenomena, right? You can have a swimming pool, literally a swimming pool filled with this stuff, and you still run across it. The same as you would if it was 6 inches deep. And so as a consequence, I don't think there has to be some size dependence. We haven't found it yet. I think the phenomena is somewhat universal. It probably does die off at some level, but I think at least for now, we think that the stress propagates as big as you can make it. But I don't have evidence of that. All right, so let's talk about activity. Now, there's lots of systems that are out there that are colloids, dead things that have been made into flowing things. But I'm going to start from biology, which is really a nice way to get motion for free, because biology is very good at it. It's very hard to engineer systems that do this. Okay, so first biology, collective phenomena. So my idea of activity is you follow simple rules, right? We've heard about rules. We've heard about lots of paradigms of how you get collective behavior. In the end, it's pattern formation, so let's talk about it that way. You have a source of energy. You have a local constraint, local rule. You say, use the energy, follow the rule, whatever it might be, see what you get. You get collective behavior. Okay, so here we go. Source of energy. There you go. You got some, anisotropic particles, and you get activity. You get an aster. You get local, active puppies. And this is what gets the undergrads interested in working in my lab. These are not my dogs. But you can imagine, right? They're following a local rule set, which says, try and eat as fast as you can and push your neighbors to the side. But in fact, you get more food, and so anyway, active puppies. Everybody loves active puppies. So I'm going to talk about 3 different classes of active materials. The 3 that I find to be the most compelling are the ones that I would call swimmers and poopers. So swimmers are sperm or other kinds of materials. There are other kinds of living organisms that can twist their bodies or twist their flagella. There are also different kinds of swimmers that have these little beating arms. They're breaking some symmetry here. The poopers are the ones that maybe have a reaction that occurs on their backside that produces gas that literally pushes them forward. So that's one class. There's active liquid crystals, which are sort of 2-dimensional and perhaps quasi-2-dimensional materials that undergo highly concentrated, flat, sort of 2D pneumatic ordering that can then dynamically change as a function of what's going on. You can get that in microtubules. You can get that in actin. I don't know what Stan was working on, but certainly these are very beautiful kinds of examples of active liquid crystals. And then there are these other materials which are active gels. So these are mostly contractile systems, things that want to pull in, like your sarcomeres. They want to pull and arrange themselves in such a way that they're sort of minimizing their shape and actually constraining themselves and actually breaking away from their boundaries. And these are active gels. The other kind are the ones that I'm going to talk about. So maybe there's 4. Okay, so Zvonimir Dojic and I are close collaborators. And he showed me this movie once at a NSF review panel, and I kind of lost my mind because it was just so amazing. So I'm going to set this up. This is a fairly big picture. This is on the order of millimeters scale. And individually, I don't know if you can kind of make it out, there's these little twigs that you can kind of see. Those little twigs are individual collections of microtubules. So microtubules are the things inside of your body that allow your cells to divide. They're the highways for your brain. It's sort of meta that we're talking about this, understanding it because the microtubules are doing their job. So we're studying microtubules with our microtubules. And what we've done is we've sort of ground everything up into a pulp. And we've thrown in basically 4 ingredients. The microtubules, some motors, molecular motors, that are on the scale of nanometers, a little bit of fuel, ATP, and a tiny bit of non-adsorbing polymer, just some stuff in the background to sort of push things together. It's more of a colloidal question. All right, that's the setup, a couple millimeters on the side. This is almost real time. Let's go. Let's go. Oh, go back. All right, here we go. All of the dynamicists in the crowd should be just jumping out of their chair. Why is that length scale there? What is going on? These things were a micron long, and all of a sudden, you get this swimming material that is otherworldly in terms of its beauty. And it restarts. So what is this thing? Is this a fluid? I don't know. Is it beautiful? Yes. Is it worth studying? I don't know. Some people thought so. So I think it's just one of the most amazing kinds of materials. This thing self-organizes into a flowing state that persists. You can make it persist for 4 or 5 days. You can just keep it doing this over and over and over and over again. Got 10 minutes? Oh, yeah, great. Okay, so here it is on a slightly more high magnification scale. Again, these are the parameters, very simple stuff, microtubules, kinesins, ATP, that's the one knob we have, this non-absorbing polymer. What's cool is that as you change the ATP concentration, it goes from dead, rigor mortis, everything stuck like a biopolymer gel, to this swimmy spaghetti, to faster swimmy spaghetti. The thing I want to point out is that the structures here are about the same. So the mechanical states that I would find are not changing, the actual physical shape of this object. If I stopped the movie, you wouldn't be able to tell me which one was 57 and which one was 1.4. That's the point. And so we can vary one parameter, which is just the speed of how this thing transforms itself.
But doesn't the one on the right have kind of a different length scale?
I think that's just maybe your eye,
Okay.
but that's what I would argue. And in fact, data bears that out. Okay, so what's missing from this? Well, of course, rheology, mechanical measurements. And so here it is in 3D. This is a three-dimensional version of this. And so we can watch what happens in three-dimensional space over time and reconstruct this material this is not a simulation, this is real stuff.
How are you doing the imaging here?
It's a high-speed confocal microscope. Yeah. Okay, so now we're going to throw it in our device. We have one hammer in my lab, and we hit everything with it. So our rheologists and microscopists get together, and we employ some really talented postdocs who started their lives at Brown, which is really nice. Thank you. And what we get is we get rheology, mechanics, and we get fluid flow. How are these things flowing? What's going on inside? Okay, so let's talk about the microscopic flows really quickly. So no applied shear, quiescent state. This is just looking at it and measuring the velocity. These are the velocity distributions. You can take the means of these things as a function of our one knob, which is just the rate at which things turn over. And in fact, you see that there's a Michelson-Menten saturation limit, which is from biology, of course. So you can only throw so much ATP in, and then it doesn't do anything anymore. Motors are limited. And so you can see, as I change the ATP concentration, I can change the velocity by an order of magnitude. It's a couple order of magnitude change in ATP, but I get an order of magnitude change in the velocity. So that's one detail. And now I'm going to do bulk rheology. I'm going to actually try and measure this stuff. Now, you're not rheologists, but I will tell you that these are the hardest experiments I have ever done in my life, because this stuff is weak. You think your brain is soft? This is 1,000 times softer than your brain. That's soft, really soft. It's hard to do, turns out. My postdoc wasted a year of her life trying to measure the system. I feel so bad. Anyway, so we had to really reconstruct things in a way that we could make a measurement. These are enormous plates. This is like taking 2 big buckets and cutting the bottoms off and putting this fluid in. And this stuff's expensive. How many cows died in order for I mean, they died because they're food, but we took their brains and, it was a lot. Anyway, all right, so I'm just going to go through it quickly. What you get in the end is a material that is elastic. When you let the ATP run out, that material, that sort of solid-like thing that's left over, is really, really soft. And in fact, it's so soft that its yield stress is 1 millipascal. That is nothing. That is like you breathe on it sideways and it breaks apart into 1 million pieces. It is the softest thing. I've never seen an M in front of Pascal, a little m. Megapascals, yes. Millipascals, no. This is, you take your hand and you push on here, that's about 1 kilopascal. This is many orders of magnitude softer than your skin. So, it's soft, it's weak. 50 millipascals, yield stress 2.1 millipascals. I don't understand these experiments and how we did them, but we did. So, all right, punchline. If you change the ATP concentration from 14 micromolars to 1,400 micromolars, so that's 1,000 times, or I'm sorry, 2 orders of magnitude. If I change at that increase at that, I get these sorts of curves for the viscosity. So again, this is water. This is the viscosity of water. This is just barely above water. It's dilute brain water is what we call it in the lab. On this end of the shear rate, so again, it's how fast I shear that top plate. At the lower shear rates, the material itself is breaking up on its own. So it looks like water. It looks like it does when I shear the crap out of it and really push it hard. It basically looks like that on its own. We can make a measurement of that viscosity. As I increase the shear rate, the viscosity of this material increases up to a point, and then it decreases. Now, remember that plot I showed you of shear thickening and shear thinning? It's exactly what's going on here. As I shear my material, it gets thicker. That's all we do in my lab is shear thickening, it turns out, for every material we're interested in. And for every concentration of the material that we're studying, as we go up in shear rate, the viscosity goes up. It goes up, it goes up, it goes up, and then it universally thins. So I can take the timescales, because of this measurement is 1 over timescale, I take tau from this, and I get, as a function of ATP, how does the timescale for the rheology look? And in fact, it follows that it decreases as a function of increasing ATP concentration. All right, so let me just skip all of this. Let's combine these things, a tale of 2 rates, right? This is literature. So the viscosity goes up, it hits a peak, so that's 1 timescale, set by the bulk mechanics. And what's going on? There's another timescale, this is rate 2. So these are these microtubules, they slide past each other because these motors are pushing them apart. And in fact, they go to a point where they fall apart, and then they find more neighbors, and they do this again, and they do this again, and this is constantly happening. That's the turnover that you see inside of the system. That's controlled by the ATP concentration. It's the unbundling rate. It's how fast they want to come apart. And when I combine these things together, very stupidly, I get a constant, which is this length scale that comes out of my problem, which tells me the length over which things unbundle. That's controlled by the ATP. Now, I'm going to show you theory, last couple seconds. A theory should be simple. That's what I learned from my advisor. And in fact, you could even, invoke some philosophy if you want. Occam's razor, right? Fewest assumptions is probably the correct one. Well, I didn't have Occam, I had David, so he had an X-Acto knife, not a razor. And so his was few assumptions can't hurt, right? So we'll make some assumptions. Our hypothesis is the following. There's 2 rates, shear rate and unbundling rate. And I'm going to say that for my system, inside, that swimming spaghetti inside of my rheometer, there exists a set of percolated paths. Those are just ones that touch the bottom and touch the top, where their local unbundling rate is slower than the shear rate. So what you would imagine is I'm shearing it, and these things can't fall apart on their own as a function of how they're being sheared, or set by this rate. So I can't get them apart fast enough. And the motors, those things that connect those microtubules together, they behave as a solid crosslink between the bundles, so I can't get them apart. So what I end up with is slow paths that look like elastic rubber bands that are connecting the top plate to the bottom plate. They resist the flow. Resistance to flow is an increase in viscosity. So those elastic paths effectively increase the viscosity. And the participation rate, that is the number that are connecting, is just a question of what rate I'm shearing at. How many unbundle? How many are solid-like? So I have these fluid-like and solid-like elements. I construct at 0 shear rate. They're all fluid-like. They all just unbundle on their own. That's low shear rate. Intermediate shear rates, I have some that are connected, some that are liquid-like. And at their critical shear rate, where the viscosity was at its maximum, I have the most of these. And above that, they just flow. I've broken everything up. So solid-like elements resist the shear as the shear rate is increased up to a critical point, and then it undergoes another transition where it's a fluid again. And so now I'm going to do some math. Doesn't matter. What I want to say is that there's a fraction of these connected paths that I'm going to consider that I can get from my velocity distribution functions. And if I do that, I can build a rheological model. It's actually a Bingham plastic. That doesn't matter either. But what that says is that it's a yield stress material. It has a fluid yield stress. The material itself, I have to push it at a certain stress in order for it to break. After it does that, it follows a very typical curve that's simply defined by the yield stress times the viscosity times the shear rate, which is a stress. And if I do that, and I state that there are two numbers in my model, that is the yield stress, which we measured before in another experiment, 2.1 millipascals, viscosity of the solvent, which is just the fluid, just water, I can build an entire model with no free parameters that as I change the ATP concentration, goes perfectly through my data. To within, I mean, this is rheology with error bars. If you ever meet a rheologist, ask them what an error bar is, they will not know. But we have error bars, and we are able to fit this very stupid model to these very complicated experiments. All right, so I'm going to conclude. Extensile active matter, very complicated rheology. It's ATP-dependent thickening behavior that we observe and we can measure. And we've looked at it on the microscopic scale too. It's quite beautiful. I just didn't have time to show you. These self-yielding gels are, in fact, happening while the shear is slow. So they want to self-disassemble. And they can if you don't perturb them. There's a characteristic length scale in the problem which tells you how much of these things are overlapping and how much they actually have to traverse themselves in order to fall apart. We were able to measure that. It's about 11 microns. And that the quiescent activity, that is the activity without shear, actually determines the rheology, which is kind of a weird thing. It's this disconnect between these two states. Okay, so these are all the people and the money, and thank you.